Hey, what's up, guys? This is Chung here again. So let's take a look at today's daily challenge. Problem number 23, merge k sorted list. So this is a very classic uh, problem, as you guys can tell from the number, right? It's pretty old one, but it's a very classic one. So basically, you're given like an array of k linked list, and each linked list is sorted in ascending orders, and you need to merge all the linked lists into one sorted list and return it, right? So basically you're given like three sorted linked lists, and then you need to return one. You need to merge them together. Yeah. So I mean, so for this one, it's the parameter is given as like a linked list, but there's some other like prim variations where this instead of a linked list, it could be a list, an actual sorted list. And the algorithm should be the same. And so linked list has its own like properties, like the values and the next, right? So which makes the implementation a little bit different, but the key idea stays the same. So for this kind of problem, the I usually solve it in two ways, right? So the first one is like we uh, merge those lists, sorted lists one by one. So we merge the first one and second one, and then we got like a new merged list, and then we merge that one with the third one, and then so on and so forth. So basically every time we only merge two sorted lists, and then in the end we'll end up having one sorted list. So and let's try to implement that real quick, right? So I think that's pretty much a very classic merge sorting, right? We have L1 and L2, right? And since this one is like a linked list, we always create a dummy, right? A list node here. Then with the current equals dummy, right? And then while L1 and L2, right? If L1 dot value is smaller than L2 dot values, we go with the smaller one. So which means the current dot next will be the L1, right? And then we move L1 cursor to the next. L1 equals to L1 dot next, right? Then else current dot next equals to L2. Basically, we're pointing the current one to the L2 value, and then we move L2 forward. And in the end, current equals to current. We move the current forward, right? So, and now when the while loop is finished, if there's any element left, either it could be L1 or L2, we just simply append the remaining of L1 or L2 to the rest to the current pointer, right? Next equals to L1, right? And then if L2, and then we do L current dot next equals to L2. Then in the end, we return the dummy dot next, right? So that's the merge function and helper functions. And then so here we simply do a length of the list, right? Uh, we do a simple check if the n is equal to 0, right? And then we simply return none. Else, we start L1 with the list 0, and then for I in range of 1 to n, right? So the L1 will be the merge of L1 and the list of I. Basically, we the L1 starts from the first one, and the second one is always the next nodes in the list. In the end, we'll end up with one list, and that's exactly what we need. So we just return L1. Yep. So run the code. Cool. So it's accepted, but it's barely passed, and it's pretty slow. So the reason being is that the time complexity for this one is actually And let's say, we have a k here, and let's say the total numbers of the list is n. So the time complexity is going to be n times k. And with the constraints of mm, of the number, so k is 10 to the power of 4, and the total numbers, yeah, as you guys can see, so the length of the list could also be up to, sorry, so then I mean the length of the list is always k, right? And then the n here is the total number of the items in those k lists here. Yeah, and this one could also be up to like 10 to the power of 4 or even more than that, right? That's why this one is kind of slow. And another way of solving this problem is by using a priority queue. So, for the priority queue, the basically we're using the priority queue to maintain, right? To maintain the smallest number among all the case list here. And every time, right, we pop the current smallest one among all the case list, and until the priority queue is empty. So, and to do that, right, besides the values that will be used to do the priority queue sortings, right, and then we also need to maintain the list itself, so that every time when we pop the current smallest one, we know which list that number belongs to, and then we can just after popping this one here, and then we can find the list itself, and then we can move the cursor to pointing to the 4 here, so that we can push this 4 into the priority queue, so that they can be sorted, right? And yeah, so that's basically the idea, right? And then in the end, we just uh, exit the while loop while the priority queue is finished, which means that we have processed all the list. So to do that, right? So we do a priority queue and dot this, and at the beginning, right? At the beginning, we're going to push each of the elements, the first element of each of the sorted lists to the priority queue, and so that they can be sorted, right? So for nodes in lists, and okay, since there could be an empty list here, right? And we just let me finish this one. So priority queue dot heap push, right? And then the priority queue, and then the value. Like I said, we need to the key for this one is going to be the node dot value, and we also need to maintain the list itself, which in this case we have to maintain the node itself, because we need the node, right, to be able to move to the next one. Okay, but since the node could be empty and the node value could throw an exception, that's why we need to do a simple check here. If the node is not empty, then we just push it into the priority queue. And then similarly, right, we also need a dummy node, right, the list node, and then current equals dummy, right, and then while priority queue is not empty, right, we just pop the current element, and then but which we don't need, and we just need it to help us to do the priority queue sorting, right? And the current one is the node and equals to the heap queue dot heap pop, right, priority queue. And so basically that's this node is the current smallest number, which means that we're gonna do the current dot next, pointing to the node itself. Okay, and after this one, like I said, we need to move the pointer, right, to the next one. So which means that if the node dot next is not empty, then we push the next one into the priority queue, right? Push priority queue dot uh, current dot next dot value, and then the node dot next. Yeah, and then don't forget to also move the current to the next one. And then in the end, we simply return the dummy dot next, and that will be our answer. Okay, so let's try to run it. Does not support between instance of this one and I think this is like the Python 3 changes here. Let me try to use Python here. Will this one work? Dummy. Never mind. I think in Python 3 here, it does not support does not support the comparison of the list node here. So because if the first one, in the priority queue, right? If the first one is the same, right? It's same, then it will try to compare the second one. So but we still need this node to be part of the items. And what we can do here is that use we can add like a dummy like integer that can distinguish each of the node, right? We can do an ID of node here. This is the Python's thing. For each of the object, if you do ID, it will give you a unique ID for this object, so that since we can use this one when to handle the duplicate key here, so that if the first one is duplicate, on the second one it's always different, so that it doesn't have to go to the next node one, it does not support to do the comparison. So and yeah, I believe in Python 2 this thing it supports this node, but for some reason in Python 3 they changed this uh this function here. So and here we also need to do this one. Okay. Uh, Seems like we have an issue here. So priority queue has to be here, right? Priority queue current 13141326 node dot next. Uh, Here I guess. So here should be node, not the current, right? Node dot next dot value. Yep. All right. So submit. Yep. So this one is much faster, right? Only less than 100 milliseconds. And the reason being is that for this one the time complexity is what? It's the n times log k. Since each number will be pushed into this priority queue once and popped once, and to maintain this priority queue, the push and pop, right? So the time complexity is log k. That's why the total is this one, which is faster. And especially when when the k is pretty small, right? And then this will basically will close to a linear time complexity, which is pretty good. And yep, I think that's it for this classic merged case sorted list problem. You know the oh well you know if this one if you're given like instead of a linked list, you're given like an actual list. You know, so for this kind of priority queue, you know what we can do is that you can simply create an index for each of the list, right? And then on top of that, you can also maintain like the pointer, right, for each of the list that can help you remember which number you're processing right now, so that you can use the pointer to 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 move to the next one. Similarly, like what we have in the node here, since in the for the linked list, all we have is the pointer to the next one. That's why we have to maintain the current node, right? And I think for this one, instead of the node itself, maybe we can also maintain like the next values so that we can avoid using this like a trick for the priority queue. I think that will also work, but I'm not going to implement that here. I'm just showing you guys the idea of this using priority queue here. Yeah, I think that's it. I'll stop here. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.